Welcome to the second session of our fifth module. So we have been discussing about Rayleigh flow. So we have drawn a Rayleigh flow, a Rayleigh line, right? Rayleigh line. So this will be H maximum enthalpy, and this will be S maximum entropy. So if heating is taking place, so actually I'm discussing about today we will be discussing about choking in Rayleigh flow. So we have studied choking in various flows already. So what will be the choking condition for Rayleigh flow? So in heating, if we are adding heat to a subsonic flow means this is m less than 1. So this is subsonic, right? So heating means the states will be shifted to right? So it can be observed that if we add heat, the Mach number increases and reaches a maximum value of 1. So if heat is added to a flow where m less than 1, then Mach number will be increased to 1. So Mach number will be 1 at this particular point. So while heating, the state will be the fluid will be moving along this line up to this point, right? Up to this point, that is entropy continues to increase to an maximum value of entropy S max, right? But if you add more heat, then it won't come this direction. Why? Because this direction means entropy is decreasing, but it is a violation of the second law of second law of thermodynamics, because while heating, entropy always increases, it never decreases. So the maximum point up to which heat can be added is this particular point in case of m less than 1. Similarly, if m greater than 1, it is added means the state shift from this particular point and it will move up to this point. Okay, then after that also, if you are adding heat beyond that particular point, means entropy will be decreasing, right? But entropy will never decrease in a process where heat is added. So the maximum point up to which heat can be added in a supersonic flow is also this particular point only, S only. Okay. So hence the flow cannot proceed after a Mach number of unity. So at either subsonic or supersonic speeds, the amount of heat input cannot be greater than a definite quantity, which makes Mach number unity at the exit. So the maximum amount of heat that can be added is such that at the exit the Mach number becomes unity. Okay. For a given initial condition length of the pipe, there is a maximum possible rate of heat addition to the gas, beyond which entropy uh, entropy entropy reaches the maximum value, beyond which entropy cannot be changed, right? So that particular condition is called choke flow. If maximum heat is added such that the Mach number at the exit becomes 1, that particular condition is known as choking. Choke flow. So the point of choking is this point. At this point, flow becomes choked. So flow becomes choked when Mach number reaches 1. So if the heating rate is, if maximum possible heat is added, maximum possible heat is added. But if you again increase the heating, means there is no change in entropy possible. So what happens is some readjustment takes place in the flow in order to accept the increased heat, like initial Mach number getting sufficiently changed, or the mass flow rate will be changed. So only by such readjustment we can add more heat. Without readjustment of flow, you cannot add heat beyond the maximum entropy value, or m equal to 1. Okay. Now students, what is a state of maximum enthalpy? So location of the examination of this particular Rayleigh line at some location, the subsonic branch of Rayleigh line, you can see that there is a maximum static enthalpy point, right? From the governing equation of Rayleigh flow, it can be shown that the m corresponding to m at h, the corresponding maximum static enthalpy value will be 1 by root gamma. Okay, that will be derived. Okay, so for Mach number below 1 by gamma, the velocity and static enthalpy increase by heating. You can see here below h you can see that while heating below, if Mach number is less than 1 by root gamma, that means below this h line, if heat is added from 1 to 2, static enthalpy increases, velocity, what will happen to velocity? Velocity also increases. Okay, but for a portion in between this, for this particular portion, you can see that after m reaching 1 by root gamma, if further heat is added, so heating is possible up to this point, right? But if you had heat in this particular value, static enthalpy decreases but velocity increases. So in between H and S, there is an anomaly, because here, even though it is subsonic branch, the variation of static enthalpy and velocity is not the same as that in the case below H. Okay, so this part has got a property, this part has got another property. So in this part, when heat is added, both static enthalpy and velocity increases, as we have studied in the previous session. But that is not the case here in between H and S. Here, when you add heat, static enthalpy decreases but velocity increases. Okay, in between H and S, static enthalpy decreases, velocity increases. So what is the reason for this particular abnormal change? What is the reason? So the effect of addition of heat to the flowing fluid causes what? So when heat is added means its fluid density. What will happen to density? Density will decrease, right? When heat is added to a fluid density will decrease along with the increase in what will happen to stagnation enthalpy? Stagnation enthalpy increases, right? Stagnation enthalpy increases when heat is added. So the decrease in density makes the velocity, when density is decreased means velocity capital V will increase, because rho V is constant. Since rho V is constant, when density decrease, velocity increase, right? So some of the heat added to the system is converted to what? Kinetic energy of the fluid, and the heat energy in excess of this amount is available for increasing the enthalpy of the fluid. So students, I am adding a Q. Part of Q is used in increase in velocity. Velocity of the fluid. Velocity of the fluid means increase in kinetic energy. Okay, increase in the kinetic energy. Part of this Q is the remaining part is used for increasing the static enthalpy, right? So the added heat will be used in two ways. One part will be used to increase the kinetic energy of the fluid, and other part will be used to increase the static enthalpy of the fluid, right? Static enthalpy is increasing means the static temperature will also be increased. So with the higher when kinetic energy is increased means velocity is increased. So with when higher velocities are attained, okay, when higher velocities are attained, addition of more heat is accompanied by much greater decrease in density. Okay, so higher velocity, when maximum velocities reach, again heat is added means very drastic decrease in density will be happening. So it requires a greater increase in kinetic energy. So there will be a rapid increase in kinetic energy again. Eventually what happens, a point is reached where the heat energy added to the fluid is completely required for increasing the kinetic energy. So when this particular h point is when Mach becomes equal to 1 by root gamma, the velocity or the kinetic energy of the fluid will be in such a situation in such a situation where it absorbs whole of the heat added to increase its kinetic energy again. Okay, so there will be no share. So completely this Q will be completely used for this increasing kinetic energy only. No share for increasing static enthalpy. Again, if you add heat, means the velocity of the flow again increases more than the Q. Okay. So അതായത് Q ആഡ് ചെയ്യുന്ന Q ഇല്ലേ, ആഡ് ചെയ്യുന്ന Q കൈനറ്റിക് എനർജി ഇൻക്രീസ് ചെയ്യാൻ യൂസ് ചെയ്യും. പകുതി ബാക്കി ഒരു പാർട്ട് സ്റ്റാറ്റിക് എൻതാൽപ്പി ഇൻക്രീസ് ചെയ്യാൻ യൂസ് ചെയ്യും. പക്ഷെ ഒരു പോയിന്റ് എം ഈക്വൽ ടു 1 ബൈ റൂട്ട് 2 എത്തിക്കഴിഞ്ഞാൽ കെ ഇ ഇൻക്രീസ് ചെയ്യും സച്ച് എ വേ ദാറ്റ് വെലോസിറ്റി വളരെയധികം കൂടും. അപ്പോൾ ഒരു പോയിന്റ് എം ഈക്വൽ ടു 1 ബൈ റൂട്ട് 2 എത്തിക്കഴിഞ്ഞാൽ പിന്നെ ഈ ആഡ് ചെയ്യുന്ന ക്യൂ ഫുള്ള് കൈനറ്റിക് എനർജി ആയിട്ട് മാറ്റാനായിരിക്കും യൂസ് ചെയ്യുക. സ്റ്റാറ്റിക് എൻതാൽപ്പി ഇൻക്രീസ് ചെയ്യാൻ ക്യൂ ബാക്കി ഉണ്ടാവില്ല. പിന്നെയും കുറച്ച് കഴിഞ്ഞാൽ കൈനറ്റിക് എനർജിയുടെ ഇൻക്രീസ് ആഡ് ചെയ്യുന്ന ക്യൂനെക്കാട്ടിയും കൂടും, കൈനറ്റിക് എനർജി കൂടും. അപ്പോൾ ഈ ഇതിനെക്കാട്ടിയും കൂടുതൽ വേണമെങ്കിൽ എന്ത് സംഭവിക്കും, അത് എവിടെ നിന്ന് എടുക്കും, ഈ സ്റ്റാറ്റിക് എൻതാൽപ്പിയിൽ നിന്ന് എടുക്കും. അപ്പോൾ സ്റ്റാറ്റിക് എൻതാൽപ്പി ഡിക്രീസ് ചെയ്യാൻ തുടങ്ങും, കൈനറ്റിക് എനർജി ഇൻക്രീസ് ചെയ്യാൻ തുടങ്ങും. ക്യൂ ഓൾറെഡി യൂസ് ചെയ്ത് കഴിഞ്ഞു. ആഡ് ചെയ്യുന്ന ക്യൂനെക്കാട്ടിയും കൂടുതൽ കൈനറ്റിക് എനർജി കൂടുന്നുണ്ടെങ്കിൽ ഈ ക്യൂവും വേണം ഇതിൽ നിന്ന് സ്റ്റാറ്റിക് എൻതാൽപ്പിയിൽ നിന്ന് നമ്മൾ ഇൻറ്റേർണൽ എനർജിയും വലിക്കാൻ തുടങ്ങും. അപ്പോൾ എന്താവും, ഇൻറ്റേർണൽ എനർജി കുറയും. അതാണ് ഇവിടെ എന്ത് പറ്റുന്നത്. അതുകൊണ്ടാണ് ഇവിടെ സ്റ്റാറ്റിക് എൻതാൽപ്പി ഡിക്രീസ് ചെയ്യുന്നത്. അതുകൊണ്ടാണ് സ്റ്റാറ്റിക് എൻതാൽപ്പി കണ്ട ഇവൻ ഹീറ്റ് ഈസ് സ്റ്റാറ്റിക് എൻതാൽപ്പി ഡിക്രീസ് ചെയ്യുന്നത്. ബിറ്റ്വീൻ എച്ച് ആൻഡ് എസ് സ്റ്റാറ്റിക് എൻതാൽപ്പി ഡിക്രീസ് ചെയ്യുന്നത് എന്തുകൊണ്ടാണ് വെച്ചാൽ ആഡ് ചെയ്യുന്ന ക്യൂ കംപ്ലീറ്റ് ആയിട്ട് കൈനറ്റിക് എനർജി വെലോസിറ്റി ഇൻക്രീസ് ചെയ്യാൻ യൂസ് ചെയ്യുന്നത്, പിന്നെയും വെലോസിറ്റി കൂടുന്നത് സച്ച് എ വേ ദാറ്റ് സ്റ്റാറ്റിക് എൻതാൽപ്പിയും അബ്സോർബ് ചെയ്യാൻ തുടങ്ങും. ഓക്കെ, അതാണ് ഈ റീജിയൻ ബിറ്റ്വീൻ മാക്സിമം എൻതാൽപ്പി ആൻഡ് എൻട്രോപ്പിയിൽ സംഭവിക്കുന്നത്. അതുകൊണ്ടാണ് അവിടെ ഒരു അബ്നോർമൽ കണ്ടീഷൻ വരുന്നത്. ഓക്കെ, now we can move to location of maximum entropy. Location of maximum entropy. Location of maximum entropy. So we knew the continuity equation, rho v equal to g equal to m dot by a equal to a constant, right? Also the momentum equation, p plus g square by rho equal to constant. Okay, so I am converting this equation to a differential form. So differential form is dp plus g square is constant, rho is a variable. So dp plus g square 1 by rho differentiate, when 1 by rho is differentiated means rho raised to minus 1 rho raised to minus 2, right? Differential d rho. So this will be the differential form of rho raised to minus 1. Okay, so I'm substituting minus rho raised to minus 2 d rho is equal to constant. When constant is differentiated means it will be 0. So dp equal to g square minus rho square and rho raised to minus 2 into d rho. So if you rearrange this, you can get it dp equal to g square d rho by rho square, right? This is the differential form of momentum equation. Okay, So since G is rho V, you can write dP equal to rho V whole square d rho by rho square, and it will be dP equal to V square right, V square d rho. Okay, so that will be dP by d rho is equal to V square. dP by d rho is equal to V square. So students, you can look at the so I will draw this HS diagram. Okay, so this is H, this is S. So you can see that in this area, the area where entropy is maximum, it can be seen at in that small infinitesimal region, the neighborhood of maximum entropy. The state of change in entropies can be seen as 0, because in this particular small area entropy remains constant, means there is no change in entropy in this particular differential or infinitesimal region. Okay, so the state here is almost vertical. The line in curve is almost vertical. So ds can be taken as 0 in the small region. Okay, in the small region. So when here corresponding to S constant or constant entropy, dP by d rho is V square for Rayleigh. So dP by d rho at constant entropy, we know dP by d rho at constant entropy is a square. We have already studied in the first module, but here it is obtained as V square. So V square will be equal to a square. That will V equal to a. That means m equal to 1. So in this neighborhood, in this region, where here maximum entropy region, m will be equal to 1. Okay, m will be equal to 1. So the maximum location of maximum entropy means maximum entropy will takes place where m Mach number becomes 1. So that this is how we derive that condition. Now we have to locate maximum enthalpy value, location of maximum enthalpy region. Okay, so we know the perfect gas equation P equal to rho RT, right? P equal to rho RT. Okay, so if I take a logarithm, if I take the logarithm, log P is equal to log rho plus log R plus log T, right? So then I differentiate this, means dP by P equal to d rho by rho plus dt by t, right? Log A is, differential of log A is dA by A, right? So you know this, right? So dP by P equal to d rho by rho plus dt by t. But students can see that in the region of maximum enthalpy value, it is almost horizontal. That means H remains constant. H remains constant means T remains constant. T equal to constant there. So T equal to constant means this can be assumed to be 0. dt is 0. So dP by P is now d rho by rho. Or dt by t is assumed to be 0. So it is approximated as 0. Okay. dP by P equal to d rho by rho. And now dP by P, dP by d rho becomes P by rho. I am rearranging this equation. So dP by d rho becomes P by rho. Okay. dP by d rho is P by rho. But P is rho RT. P is rho RT by rho. So rho and rho cancel. So dP by d rho is RT. Okay. dP by d rho is RT. But already we have found that for Rayleigh line, dP by d rho is V square. dP by d rho is V square. Okay. So substituting here, it is V square, capital V square, velocity square. you will get V square equal to RT. So M equal to V by A, right? V by A. That is, here V is equal to root RT, right? So root RT by A is root gamma RT. So what remains? Root RT cancel. What remains? 1 by root gamma. So at constant enthalpy, maximum enthalpy value, Mach number will be 1 by root of 1 by gamma. Okay, or 1 by root gamma. 1 by root gamma. For air, gamma is 1.4, right? So M at maximum enthalpy value will be 1 by root 1.4 and it will be around 0.84. So Mach number at maximum enthalpy will be 0.84 for air. Okay. So that's it. For the time being, we will stop this session. And in the next session, we will learn about Rayleigh relations for perfect gas. Various relations: pressure ratio, velocity ratio, density ratio, okay, temperature ratio, stagnation temperature ratio. All these relations will be discussed in the next session. Okay, thank you.